So in Chapter 16, I'm just going to take a couple of the sections out of Chapter 17 and talk about some of the subclasses of lipids. Now, the lipids that we're going to be focusing on will be primarily triacylglycerols, and then we'll talk a little bit about steroids. But lipids as a whole are a large class of biological molecules that will contain very particular kinds of groups. And we're going to talk about fatty acids as being components of triacylglycerols. And we'll talk about the steroid molecules like cholesterol will be our primary focus, but I'll also mention bile salts and, of course, the steroids that you guys are typically exposed to, which would be the sex steroids for males and females. So lipids are molecules that are soluble only in organic solvents. What that means is that they're going to be primarily hydrophobic in nature, and so they are not going to be soluble in water. So anytime that we want to isolate lipids for any particular reason, we're going to have to use these organic solvents to isolate those or extract those from cells. So the lipids that we're going to talk about are going to be primarily fats and oils, which again are chemically and structurally, they're referred to as triacylglycerols, and steroids. Now there are other important molecules I'll briefly mention and their roles in nature, but we're not going to spend a lot of time talking about anything beyond that. So this is a schematic diagram of how lipids are classified, how they're broken down. So we're going to start with kind of lipids in general. That's just the kind of properties that we've been talking about and some basic roles of those in the cells. And we're going to talk about the components of a subset of those called fatty acids. So we're going to talk quite a bit about the structure of those and how fatty acids are joined with a glycerol backbone to form triacylglycerols. So these will be the most important class of lipids we're going to talk about. I will mention the health ramifications of molecules called prostaglandins and the special kinds of fatty acids that are required to make those. And then we'll also talk very briefly about steroids, and then specifically within that subclass, more details about cholesterol in general. So fatty acids are the molecules that are joined together to make the triacylglycerols that we'll talk about in the next section. But right now we're going to take a little bit of time in thinking about what fatty acids are. Fatty acids have the functional group that's the same as that of the carboxylic acid. So they are technically a type of carboxylic acid. And they've got a very, very long hydrocarbon chain, usually between 18 and 20 carbons long, that extends beyond the carboxyl group that you guys identify as carboxylic acids. Now, because of the long hydrocarbon chains, they are insoluble in water, and the properties of that fatty acyl chain is going to cause us to classify a fatty acid as either saturated or unsaturated. So these are going to be the different ways that we can depict fatty acids, at least as far as their chemical structure is concerned. And right here is the typical group that you identify with a carboxylic acid. So this is what is going to be at the beginning of every fatty acid. Okay, it's going to be this carboxyl group. Now, of course, it is going to have the properties of carboxylic acids, which means that this OH can be a point of reactivity with other molecules, and that's going to become really important to think about. This is the other way that we've kind of depicted fatty acids, carboxylic acids as the COOH, understanding that this one oxygen is this double bond O right here. This is going to be the condensed structural formula for a fatty acid. So again, this is where you've got all of the details about what the fatty acid carbon chain is going to look like. More often, because this can get a little bit cumbersome, more often we represent fatty acids using the line diagram formula. So this is going to be what we're going to look at most of the time as we think about what these fatty acids are and what they look like. So a fatty acid, again, is going to have this long hydrocarbon chain, and many fatty acids will have every single one of those carbon-carbon bonds as being a single bond. And that's how we identify, or how we define, a saturated fatty acid. So it's saturated because it contains only carbon-carbon single bonds. And what that means is that these chains can line up next to each other really, really effectively. And because they can pack together in that way, they provide lots and lots of points of interaction. Now that's going to have ramifications on the way these fatty acids look at room temperature, or even the way they look in our bodies. So saturated fats are the kinds of fats that you see when you see a big old ribeye steak down at the IGA. So all of the white that you see, and all the caramelized, ribbons of white that you see interspersed with the muscle of the steak, all of that is indicative of saturated fats. So the fats that are present in a steak are going to be primarily those with single carbon double bond, or carbon-carbon single bonds, with no double bonds. And what that means, because of the high interaction, that's going to mean that the melting point for that fat is going to be at relatively high temperatures. So they're going to be solids at room temperature, which again is what you're going to see if you have a big old steak that you have sitting on the counter. Now the properties, of course, are going to be related to the length of the chain of the fatty acids. So the longer the chain gets, the more points of interaction, and therefore the higher the melting point will be. So animal fat, like the fat that we see in a steak, is primarily stearic acid, which is 18 carbons long. Again, you're not going to need to know the names of these. You're going to want to make sure that you understand the properties of how these fatty acids behave based on whether they're saturated or unsaturated. So smaller chains are going to have smaller melting points than lower melting points than larger chains. Now unsaturated fatty acids are going to be fatty acids that have at least one, and sometimes multiple, carbon-carbon double bonds. Now in nature, those double bonds, or the fatty acids, are made in a way that those double bonds are going to be in the cis configuration. So remember that cis means that the fatty acid chain is going to be coming off of those two carbons participating in the double bonds on the same sides. If you take your double bond, you slice it down the middle like this, both chains come off the same side. If it was a trans version of the acid, it would be coming off of opposite sides. So again, here's going to be our plane of our bond right there, and in this case, the two portions of our hydrocarbon chain come off opposite sides. So this is the trans configuration. Again, in nature, we see the cis configuration for the double bonds in naturally occurring fatty acids. Now what that means is that these guys are not going to be able to pack together very effectively. And so that's going to have a huge impact on the way these fatty acids relate to, or as physical properties, relate to those of saturated fatty acids. So if you look right here, we saw the 18 carbon long saturated version of a fatty acid on a couple of slides ago had a melting point of 69 degrees. If you add only one double bond into that hydrocarbon chain, that has a dramatic reduction in the melting point for the fatty acid. So we go from 69 to 13 degrees with just one kink in our fatty acid. Now if you have multiple double bonds, so it's a polyunsaturated fatty acid. Again, if you've got three double bonds, like we have in linoleic acid, it's still 18 carbons long, but the melting point is now negative 17 degrees. So if you've got two double bonds with 18 carbons, it's negative 9. If you have three double bonds, it's negative 17. So the introduction of double bonds has a dramatic impact on the melting point, or the physical properties of the fatty acids individually. Down here we can see a fatty acid that we find, one of the polyunsaturated fatty acids that we find in fish and in eggs and in some kinds of meats, and that has a melting point of -50. Again, because every time you introduce a double bond, you introduce a kink that will prevent those molecules from interacting very effectively with each other. So here again, we've got the kinks depicted in our line diagrams. Again, they're going to prevent these guys from lining up very well and packing together. So because they can't pack together, there are going to be fewer interactions. And the fewer interactions from molecule to molecule is going to lead to a lower melting point. So unsaturated fats, and especially polyunsaturated fats, are going to be liquids at room temperature. So if you think about a bottle of olive oil, for example, a bottle of olive oil is going to be a liquid sitting in your pantry. Unsaturated fats, because they can't pack closely together, are not going to have the interactions that the saturated fatty acids that are found in a big old steak would have. Now there are very particular polyunsaturated fatty acids that play an important role in being building blocks for molecules referred to as prostaglandins. So prostaglandins have 20 carbon atoms in their fatty acid chain, and they've got very particular properties that are listed here. Now you don't need to memorize these different properties, but if you were to see one, it'd be a good idea for you to be able to recognize that as a prostaglandin. So arachidonic acid is the building block for these fatty acids, or for these molecules, and you'll see that they've got a double bond O at carbon 9, and then we've got hydroxyl groups at very specific locations. So hydroxyl group at carbon 11 and carbon 15, and then a double bond at carbon 13. Again, the carbon 1 is going to be the one right here at the carboxylate group. So this is carbon 1. So you count down, this is carbon 11, this is carbon 13, and this is carbon 15. So prostaglandins are synthesized from fatty acids that we get in primarily through vegetable oils or fish oils. Now in vegetable oils, there is a class of fatty acids called omega-6 fatty acids. Now the omega-6 name comes in from the fact that we begin counting at the opposite end from our carboxyl group. So remember, the IUPAC name starts with the carbon 1 right here. But with the omega designation, we think about the number of carbons from the end of our fatty acid chain. So this is going to be carbon 1 in the omega numbering system, and omega-6 fatty acids have a double bond that begins at carbon 6 from the end. So if you count 6 carbons from the end, you get to this carbon, and that's the first of the carbon-carbon double bonds present in the molecule. So omega-6 fatty acids are present in vegetable oils. Omega-3 acids are found in fish oils. Again, this is why people stress the fact that you should eat fish a couple of times a week, because our bodies don't have the capacity to synthesize these fatty acids on our own. We have to be able to get those from our diet. So omega-3 fatty acids are going to be 3 carbons from the end. So carbon 1 is right here, carbon 2, and carbon 3. Again, it's going to be the first of multiple double bonds present in these very special polyunsaturated fatty acids. So these are the building blocks for prostaglandins. Prostaglandins are the molecules that are produced when there is a damage that's done to your tissue. So these prostaglandins are the molecules that are going to result in the symptoms that we experience. So pain, fever, and inflammation. So anti-inflammatory medications, so anti-inflammatory drugs like aspirin, are actually going to block the ability of your body to take these fatty acids and convert them into prostaglandins. So that's why something like aspirin works to alleviate our symptoms, because it's alleviating the molecules that are causing the symptoms that are the result of the injury. So understanding how these molecules are made and how they cause the symptoms of pain, fever, and inflammation can help people in the pharmaceutical industry to develop medications that will block the ability of your body to take these polyunsaturated fats and synthesize these prostaglandins. And aspirin is going to be a very important example of a medication that accomplishes that for us. So again, these are just examples of some of the very important either omega-3 or omega-6 fatty acids that we need to acquire from our diets. Again, you don't need to know these, but just understand the significance of the multiple double bonds with respect to the physical properties of the fatty acid, and then the importance of these molecules in the synthesis of other biologically important molecules or biologically relevant molecules when it comes to medicines and the health of a human being. So this is going to complete our discussion of the properties of fatty acids for now. And then in the next PowerPoint, I'm going to talk about how these fatty acids are joined together with other molecules to make some very important biologically relevant molecules.